Okay, and you, I need to be able to share my screen. You have to, that says the host is disabled participant
Yes.
screen.
So go ahead. Go ahead.
Okay, I'll try it again. All right, seems to be working.
Yeah.
There we go. All right, so everybody should be able to see the screen. And I tried to make my abstract and the title interesting. It's been several years since I've been invited to give a presentation at this seminar. Obviously, we're desperate, and that's why I'm doing it now. So, and I'd like to just point out right here on this slide that we've got two kinds of geometry here. We've got the geometry in the clouds and the trees, and we've got the geometry of the building. And we are much more apt at describing this kind of geometry in the building. We've got a nice little hexagon and walls, and than we are of doing, say, the clouds. And what we're going to be concentrating on today is the clouds and how we can make your research stand out with this. Well, all right, surfaces cover everything. And in material science, if we think about where surfaces are important, heat and mass transfer, so carburization, for example, wetting, adhesion, fracture, fatigue, friction and wear, all important topics in material science, and all are very much oriented towards the surface and influenced by the surface topographies. In fact, the surface is the only thing we can touch. It is the only thing that we can see unless we're dealing with a transparent material. And so we're stuck with dealing with the surface. The interactions take place at the surface, heat and mass transfer take place across the surface. In manufacturing, we would like to know how to make surfaces with desired properties. And that depends on the designer speccing the surface properly. And if we look at some of the other sciences like anthropology, archaeology, forensics, geography, oceanology, and I suppose we could throw in cultural heritage preservation as a kind of science. Those all have important surfaces in them. Actually, by the way, for cultural heritage, just down the street from us at the Worcester Art Museum is one of the best restoration labs in the world. So there's different kinds of metrologies we might be looking at. So we've got, on one hand, dimensional that we're kind of used to, although we've struggled a bit. WPI really doesn't have a good dimensional metrology setup. And then the surface metrology over here on the right. Dimensional metrology, we're dealing with tens of thousands, and we're characterizing smooth shapes. So we're trying to see how close things are to a cylinder. Surface metrology, we're thousands to millions of measured or sampled heights. And so down here is a sensifar, for example, that very quickly measures 1 million elevations on the surface. So we've got different challenges in how to deal with the results of these two. Obviously, we're going to concentrate on the surface. So when we look at a typical surface measurement, conventionally, we use profiles. And so here's a profile from a turned surface, and we've got thousands of measurements. And usually we use elevation Z and horizontal X. And then if we do an aerial measurement of a surface, then, so this is a turned surface, and it might have a profile that's very similar to this one up here. And the spatial variables are X and Y, and then vertical is Z, or the heights. Now, this is much shorter, so going across here, we've got about 5 feeds, and here we've got many more. So these tens of thousands are spread out over longer distances, and here we got X and Y's. But anyway, so this is more conventional, and we're moving towards more surface measurements, but profiles are still widely used in industry. So what is surface metrology? Well, we've got some sort of process, could be a manufacturing process, could be wear, corrosion, all kinds of things that impart some kind of topography to the surface. It's impossible really to do anything to some material without changing the topography on the surface. And then how is it going to perform? What kind of behavior does it have? And that's influenced by the topography. Now, the topography, at least at sufficiently fine scales, has some irregularity to it. And that's what makes it interesting and challenging to characterize. So in the surface metrology, we measure and then characterize the surface, analyze and characterize. And this is largely what we're going to be talking about. And so we've got these thousands to millions of height samples. So every time we measure a height, we're sampling the height someplace on the surface, hence the term, that particular use of the term sample. So surface metrology systems, we might have a surface or a replica, because sometimes we're dealing with, like we've measured for NASA, we were working on pavements of runways, and it's inconvenient to bring the whole runway into the lab. So we would work with replicas or bring the machine out onto the runway, which we did as well. Anyway, so we have some measurement instrument measuring the actual surface of interest, or perhaps a replica. Then there's some sort of analysis and characterization that is software, and often this is packaged with the measurement instrument. So these may be kind of blended together. And the different applications, so process and product design, production, quality assurance, and the different sciences like material science. Now, roughness is a word that we throw around, and it can mean different things to different people, and it's used in different ways. So let's take a careful look at this. Sometimes, for some people, it's just fine scale topographies. Sometimes this is the deviation from an ideal surface, and that's actually a definition that's used in some of the standards, where the ideal surface is a cylinder or a plane, or a sphere, if we're looking at like a ball bearing. And these kinds of surfaces, planes, spheres, cylinders, don't actually exist in the strict sense. We try to make things as close as we can, but they really just exist in our imagination. So irregularity, we've mentioned already. So when surfaces are irregular, we talk about them being rough. Formally in the standards, if we remove form and waviness, and I'll be talking about these two in a moment, that is technically roughness. And then lots of people will say, oh, the roughness is 10 thou. And so they're probably referring to 10,000ths of an inch RA when they use it that way, but they may not be knowing it. So so just so you understand how people use it, RA is going to be from a profile, and SA is going to be from a surface. A typical question somebody might ask, which surface is rougher? Well, it depends upon what you mean by roughness and how do you characterize it. So do you know what you mean by roughness? So this is meant to get you thinking about this, but we're going to focus this morning, or this afternoon rather, on irregularity. So are you bothered by irregularity? Those were old ads for laxatives, but okay. So what produces value in surface metrology? Well, for commerce, for buying and selling, repeatability, reproducibility. So I can ask you to make me a part with a certain surface, and you deliver it, and I check it, and we both agree that it's within the spec, and then I can pay you for it. So and an awful lot of our standards work is directed at that. We're going to be talking today about ability to discriminate with confidence, or differentiate, or discern, being able to tell surfaces apart. Clearly that has roles in quality assurance, but it's also important in anthropology, archaeology, and forensics. Can we tell this bullet, can we tell which bullet a gun came out of? Can we tell what the stone or bone tool was used for that was made years and years ago? Or can we tell what critters have been eating? We'll touch a little bit on some of these. The other thing is to discover functional correlations. So can we, as engineers, we like to be able to predict things. So if I design a surface this way, how is it going to behave? And how should I process it to get it to do that? So this is important, obviously, in dimensioning and tolerancing roughness, but it's also important in more physical sciences. And we'll discuss a little bit more about that. So these are the two things we're really going to be looking at: discrimination and correlation. So central problems in surface metrology. Okay, so we've alluded to this in engineering, and I'll talk more about that. Science, discovering the past, but understanding surfaces in the sense of the physical sciences as well. And cultural preservation. So records of the past. It's sad actually to go for a walk out in the Tuileries outside the Louvre and see how tough the acid rain has been on the beautiful statues that they have displayed out there. And lots of our archaeological treasures are being destroyed by the air and the rain. So as we want to look at these, correlations are important for the product design, process design, for discovering the past with forensics. How hard did this person lean on the tool, for example? It's something we've looked at. So understanding the surfaces like a wetting and heat transfer, mass transfer, and tracking degradation. So correlations are important there. Discrimination, well, quality assurance and quality control. Is this surface good or not? And what do we have to do to fix it? Understanding the surfaces, discrimination is important there. And looking at records of the past. So one of the key questions is, how can we characterize irregularity? To understand how the surface was processed, predict how they're going to perform, and to find strong correlations and confident discriminations. And so these are coming up, and we have developing and developed devices. CT scans are getting better all the time and are important in looking at additive surfaces, for example. Atomic probe microscopes to get down to the very fine scales where there's lots of important fine scale interactions taking place. A little bit coarser, the measuring microscopes like the Sensifar that we had at WPI, the once and future Sensifar. It's been moved out temporarily because nobody can get in to use it anymore. Terrain mapping is another interesting one. So there's a wide range of scales here, from atomic really to planetary. So how do we do it so we can use these things productively? So if we look at historically where we're coming from on this, so surface roughness measurement and characterization goes back to the 1930s. And one of the first things people did was calculate the average roughness. So we're dealing with a profile with a number of distinct height measurements. So for the SA, which would be over a surface, and the RA, which is over a profile, it's the arithmetic average. So, and we take the absolute value. So think for a minute why it might be important to take the absolute value. So we're dealing with displacement from a mean line. There's negative points and positive points. If I really have the right mean line and I add these all up, keeping track of the sign, not taking the absolute value, they should add to 0. So I have to take the absolute value, otherwise this is a meaningless exercise. So that is the most used topographic characterization parameter, RA or SA. Um, and the one thing to keep in mind, this comes to us from the 30s. Now we have to keep using this. I'm going to be showing you some more advanced ways of characterizing the surface. But to tie in with the past, it's important to continue to use RA or report RA or SA. The root mean square, also standard deviation. Because what I've done essentially by putting a mean line in here is I've subtracted the mean. So all I have to do is take the z values and square them, and then I've got the standard deviation. So this is the first statistical moment. This is the second. You can also do the third and fourth for skew and kurtosis. But the thing to keep in mind, a couple things, when I'm dealing with the average, is that one big mountain looks like two little mountains. And since I'm squaring it or taking the absolute value, it's like two little valleys. So we can imagine that these three surfaces would behave very differently in all kinds of situations. But let's see, I thought I had one more thing there, sorry. They would be, so you might want to keep your system muted. I heard somebody there. If there's something important, maybe you can monitor people putting up their hands.
I'm checking that.
Okay. Yeah. So if you could stop me, and if you have, or if somebody else needs to stop me, turn on your mic, but you may want to keep it off. So in any event, we would have the same RA or SA or SQ or RQ for these three surfaces, but we could easily imagine that they're going to behave very differently. And what I'm pointing out here, something we may get back to, the sampling interval is what we call the distance between two height samples. So in surface metrology, we're using sample much different than we usually do in material science. Material science, we call a sample almost anything we put under a microscope. And often it is. It's inconvenient to bring the whole ship into the lab, so we take a sample of the hull and then bring that into the lab and polish it up and measure it. But so here we're using sample more in a different sense. Okay, so some other height parameters. So here's a cartoon profile, and we have a certain length on this. We have the mean line. And the RT is frequently used. That's the peak to valley distance. So it just takes the lowest valley and the highest peak. The RP is the maximum peak height. So this is going from the mean line up to the peak. And then RV is the valley depth. So the valley depth plus the peak height should give us the maximum peak to valley over some length that we're evaluating from a measurement. So there are some variations on this. You'll see RZ sometime, and this means that we break this profile up into several sampling lengths and then do the maximum peak to valley and take the average of those. And same thing for the peak height, although we call it RPM and then RVM. So yeah, for aerial measurements, as I said, we'd have an S. Now, note, there is no spatial knowledge contained in any of these. It's strictly heights. So I could take all my height measurements and reorder them any way I wanted, and I would have all of the same values. So I could reorder them somehow so I have much sharper valleys or sharper peaks. And we could imagine the surface would be much more dangerous for fatigue, or much better for cutting or wear or grinding if I had sharper peaks. But I couldn't tell the difference by using these parameters. So let's take a look at a very simple exercise you could do in Excel. And we'll just take a look at a sine wave, and we can calculate the different parameters for that. So the RQ comes out to be 1 over the square root of 2, which if you're good at math, you could predict. RT, very simple, peak to valley, and RA, you just take a whole bunch of these heights and sum them up. All right, so let's consider that. And now let's add to it, or let's consider another profile with a much smaller amplitude. Now, usually in surfaces, they do come out like this. So the largest wavelength is also the largest amplitude, especially over some interesting scale range. So we can see that this has a much smaller peak to valley, much smaller RA and RQ. Now, if we add these two together, and so I've carefully tried to do this, so I've got blue and red adding to purple, but that doesn't look very purpley, but that does. In any event, so this might be a surface where we've got a small wavelength superimposed on a larger one. And what happens to RA? Look at this. RA is exactly the same if I add the little wavelength on the big one or not. Now, the little wavelength, so this could be, let's make a surface so it's glossy or matte. This could be the part that makes it matte. That could be what we're interested in. And RA isn't going to help us at all in distinguishing those two. So anyway, so there's a little example. Now, we do filtering, and this is part of the standards. And this is often in our sort of vocabulary. So we filter out typically two scales to get at the roughness, a larger scale and a small scale. So here might be the roughness on the full range of wavelengths in a surface measurement. So these finer scales, sometimes we call them noise. Sometimes they're filtered out because people like to use calculus and pretend that what they're looking at is a function that they can write down, in which case then we've got to get rid of some of the choppy stuff. So the next largest scale would be waviness, and then the next largest scale would be form. So waviness also takes out a chunk, and sometimes the upper end of roughness can equal the lower end of waviness. I think that's usually the case, but it doesn't have to be that way. So what we're looking at when we look at roughness, by definition in the standards, is a range of scales between this very fine scale that is often filtered out, and then the boundary often with waviness. So form would be, like it's cylindrical. Now waviness, the one thing that I've heard that waviness is a good predictor of is noise and bearings. So this is at a larger scale. The roughness can be very important for holding lubrication, say in bearings. And so these are effective in some things, particularly in the automobile industry, in sorting this out. And that's because the automobile industry had so much impact over development of standards, particularly coming out of World War II, when a lot of this stuff got developed, and particularly in the United States. So here we can see there's the profile that we were looking at before for a turned surface, and here with a certain, and here's the filters for this waviness. And so we can kind of see, yeah, the waviness fits. And then what's left over basically is the roughness. Slightly different symbols are used here. So there we have the actual measured surface, the waviness that's filtered out to get us to the roughness. Now, if we take a look at the filtering, filtering can have a large impact on the result. And often at high-level international conferences, I've seen people present roughness results, and you ask them, so what did you use for a cutoff filter for the roughness? A very important question. So often these researchers throw in roughness and have little idea what they're talking about. And this is one of the manifestations of it. you need, if you don't report the filtering cutoffs, you really haven't told us anything meaningful. So by changing the filter cutoff from 0.25 to 0.8 millimeters, the average roughness changes 41%, and this is what people report. So if you don't tell me what the cutoff filter was, your results are kind of meaningless. So traditional surface metrology. Traditionally, it's usually profiles, although people are doing more with surfaces. It's characterized by height statistics. So this largely or completely ignores spatial information. Very crude geometrical characterization at best. Large bandwidths. So bandwidth, when we're talking about frequency, is the distance between the low frequency and the high frequency. And so we lack any specificity in scale, because when we're talking about frequencies or wavelengths in the surface, one is the reciprocal of the other. We're talking about a very narrow window that specifies perhaps scale. In this case, we've got large bandwidths that we're looking at, and so we're not very specific with respect to scale. So here's an important piece of advice if you want to make your research stand out with surface metrology. Do not just select any old height parameter from the 1930s to use with a 21st century measurement. If you want to have some idea, I guess, of how your what sort of performance to expect in terms of being able to discriminate or differentiate, imagine you take a modern high-performance car, like a nice Maserati or Porsche, and you replace the wheels with ones from the 1930s. Obviously, it's going to impact the performance, and you won't be able to do nearly as well as if you also had modern wheels on it. So this is sort of what it's like pairing up a modern instrument with a parameter that's 90 years old. So select or develop parameters that make sense from fundamentals of science and engineering for your application. And that'll help make it stand out, because so many people are just showing RA and don't even give us the filtering lengths. So multiscale analysis, this has been largely developed at WPI, particularly the geometric multiscale analysis. And we've had a patent, and it's in the standards, and it's actually the stuff we've developed is being used literally all over the world. And so what this is we're looking for analyses that are supplied systematically over a significant range of scales. So we're going to look at scale specificity that we didn't look at before. And we need many more than the traditional 4 ranges of scales that we were just looking at. So these are much too coarse to qualify as true multiscale analysis. We need characterization parameters that are computed across a range of scales. And then we need to do correlations and discriminations based on scale. So the characterizations and multiscale characterization change with scale in a deliberate, detailed, systematic way. And then we're going to do scale-based discrimination or scale-based correlations. And I'll show you some examples in a moment. Now, historically or conventionally, there are a number of multi-scale things that you could use. One, you could adjust the filtering, the conventional filtering, to do multiple band passes. And I'll show you an example of that near the end of the talk. Autocorrelation function is Fourier's structure function and wavelets are all ways that we get from mathematics, and they're convenient because they're included in lots of software packages. So there's really no sweat. You just take your measured data and then put it into some mathematical package, and you can put this stuff out. The things that these are lacking are clear physical interpretations. So these were all largely developed at WPI. Slope scale we haven't done much with, although it's closely related with area scale. So these are done systematically over different scale ranges. So length, this sort of comes to us from Coastline of Britain problem. Maybe some of you are familiar with that. It's called Richardson compass, or the coastline method. And that looks at the length of profiles. Area scale just takes that up another dimension and sort of plays on, Vermont would be as big as Texas if you flattened it out, which turns out not to be true. Slope scale is similar. At a large scale, most of our surfaces have little slope to them, or none, but as we look at very fine scales, we notice that the local slopes are much steeper. Filling scale, how much stuff can you fit into the roughness on a surface? And then curvature scale, and we'll look at that in more detail in a moment. So to do a multi-scale analysis, some people think you need to take multiple measurements at different scales. You can, but all of the microscope systems that I've worked with change when you change the lens or even the electronic zoom. And so that the multi-scale analyses don't overlap always as we switch the scale. The RA may appear to, but that's because it's so non-critical. So for multi-scale, I discourage this. And there are multiple scales in a single measurement, starting at the sampling interval and going up to the size of the measurement. So that's why there's a circle around this one. This is the one that we prefer at this state in microscope development. Anyway, so from these multi-scale measurements, or exploiting the different scales in the measurements, we can do multi-scale characterizations. And then we can use the multi-scale characterization and multi-scale analysis of discrimination and correlation. And then we can look at, then we can see where we get the strongest correlations, the most confident discriminations, at what scale. And I'll show you some examples of this. So after doing length scale, which I started doing in Switzerland, and also began a crude area scale in Switzerland, I came to WPI in 1989 and found that we had lots of very good programmers as undergraduates, and we started working on area scale, and it's now in international and national standards. And so what it's based on is a tiling algorithm. We use triangular tiles, and we look at the surface with all the ups and downs, and then normalize it by the projected surface. So the projected area here is staying the same. This is a measurement with finer and finer tiles, and we can see that the number of tiles, of course, goes up as they get smaller, but it goes up by more than it would if it were a smooth surface. So the relative area tells me, in this case, I've got now 0.11% more area than I had well, almost, anyway. Relative area goes up, scale goes down. Now, this doesn't appear to be going up very dramatically, and that's not the key question. The key question is, can this help us discriminate or differentiate or discern two surfaces or two groups of surfaces, or can it help us with correlations? So here's another example. This is a very early one, and as a result, it's the one that we often put in the standards for area scale. Here's the tilings, and this is a diamond coating on a silicon substrate measured with a scanning tunneling microscope at UNC Charlotte, where I had some friends. So using large triangles, the relative area is fairly small, and here you can see we've got almost 50% more area than we did at these larger scales. The scale here is in the thousands of square nanometers, or fractions or whole numbers of square micrometers. So as we take a look at this surface and do a plot, let's take a look at a bigger image. We can see here's the scale, log scale of the scales, starting from 10 square micrometers going down to less than 1,000 square nanometers. And here are the relative areas. So very smooth surfaces should be approaching 1. And so that's what we're seeing. At the largest scales, the surface looks fairly smooth. And then we have this region where and this is a log-log plot, where this seems to be a constant slope. And so this is going up and showing us that it's got sort of repeating patterns of little pyramids over big pyramids. And we can kind of see that. So here's the scale of the little pyramids or little crystals on big crystals. And then at the lower slope, when we're tiling, or the finest scales, we have a lower slope. And this comes from the tiles now being smaller than the facets on the crystals. So here we can see some crystal facets. And now we're tiling on those. And those are relatively smooth. So from the point of view of irregularity or complexity, it is related to the slope of these curves. The greater the slope, the greater the complexity. And that's what we're seeing here, or greater irregularity, if you like. So let's see how we can use this to distinguish two surfaces. So we measured surfaces made by fused deposition modeling. So this is where we lay down a semi-solid polymer, and we hope that they stick together, and we keep just putting them down. One of the interesting things is we note that this is almost a reflection of a machine surface. So the machine surface has got relatively sharp little ridges, and this has got relatively sharp little valleys. So caution, this is going to be more susceptible to fatigue. But as we lay these down at different thicknesses, here we're comparing two different thicknesses in the relative areas on several measurements. So we can do some statistics. At the large scales, we're getting about the same thing. And so they're kind of overlapping. But then at some scale, they're clearly distinguishable by their relative area. So here, multi-scale. There's a whole bunch of scales. We're calculating the relative area at scales, and we can take a look at each scale and see what's going on here. So, so we don't have to do filtering. Now, my friend Professor Bigarel from Valenciennes in France points out that this is essentially a low-pass filter. So if I have a large bump at a high scale, the increase in relative area from that stays with us all the way through to the finest scales. So here are the same two surfaces, and here we're looking at the complexity. Now the complexity is the local slope on the area scale filter. So this is similar to a fractal dimension, and this is more like a bandpass filter because the slope is not influenced by what's happening out here, unlike the relative area. So we see a different kind of result here, just telling us about the irregularity of the surface in that neighborhood of scale, essentially. Now, we can calculate the mean square ratio. So this is an F test. This is a test for statistical discrimination. And the mean square ratio has limits that tell us how confident our discrimination is. So if we want to discriminate with 99.9% confidence, meaning that we would be able to distinguish these surfaces 999 times out of 1,000 if we did a similar test. Here, right here, now there we're going to be doing better because this is the cutoff limit. But this is scales where these surfaces can be discriminated. And here are the scales where they cannot be discriminated with this level of confidence. So, and if we remember right, we had a certain amount of overlapping here. And now we are seeing the how we can discriminate. Here's another example. That the previous one was done at WPI, and so this one was done in Sweden by some friends there, and they're looking at complexity and the scalable, and they're trying to distinguish milling and hammering of surfaces. So hammering is like a kind of shot peening effect to impart, for example, a residual compressive stress. And how are the surfaces different in terms of their roughness? So we're able to identify a scale below which you can tell how the hammering has modified the milled surface. Here's another example using a multiscale analysis. And this is a slightly different kind of analysis. And it's made for CT scans. So here is computer tomography result from a measurement. And these are, we're looking at here comparing 3 different structures in a multiscale sense. So here's how and he calls it the relative internal area. And this was Jan Cuisenet who did this at the ENS Cachan at the time. And this is one of their top engineering schools where many of the professors, engineering professors in France, get trained. And so we can see these 3 different patterns of building additive structures are distinctly different, and their ranking changes at a certain scale. So right here, they're not distinguishable, but the rank that you have here is the opposite of the rank that you have out here. This is one of my favorite. It was also done with a team at ENS Cachan in France at the same school. And here we're looking at the fatigue limit on milled surfaces. So we have surfaces that were milled with different conditions, fatigued in 4-point bending. This was all done in France. And this was somebody's doctoral work, just doing this part. And then Margot Valouz came here and worked with us one summer. And we calculated curvatures based on an algorithm that was developed by our undergraduate students. And many of you know Matt, and so he was one of the ones that worked on this. Anyway, so we calculated the curvatures, and curvature changes with position and with scale, unlike the relative area that's calculated for the whole surface. And then studying the correlation strength as a function of scale. So this is multi-scale, topographic, and regression analyses that we're going to see. This, I think, is an important work because it shows the importance of some details in this. So anyway, there were 7 or 6 different surfaces. They were ball and milled in different ways, not all of them different, because some were stress relieved and some were left as measured. So here's 2 different surfaces to show you how different it is when you change this angle with the ball and mill. So this surface was 3 degrees and stress relieved and loaded in a certain direction, and this was 45 degrees and makes a much nicer kind of large scale feature on the surface, and was loaded in a certain direction. So the thing that Matt Gleason worked out very early on in his undergraduate career at WPI and subsequently presented at an international meeting was how to calculate curvature or how to use Heron's formula to calculate curvature from our profiles in a way that fit well with the other multi-scale work that we were doing. And anyway, so here's just some details of that. and that's published in papers. Now here's a nice representation that Matt Gleason worked out. So he's making these maps, and the curvature changes with color, is shown over here. So curvature is the inverse of radius. And as we get to large scales are three heights that we use to characterize the surface, get further apart. So we only get fewer curvatures near the middle. So, and here's the end of this one down here, which goes to one curvature that we can calculate reaching across the entire measurement. So in this, while we were working from 3D measurements, we extracted profiles in the direction appropriate for the loading. And so we can see these patterns of position along the profile, scale, and then curvature in the vertical. And so they make rather nice looking little diagrams. And they're also kind of revealing. Now the fatigue tests are extensive. So there was, I think, 80 surfaces that were fractured and 4-point bending. And here, so for polished specimens, here's what the fatigue limits were, and then for different milling. So here you can see where the how the curves were generated. So when Margot came, we knew that we'd like to find the largest curvature because that would give us some indication of the stress concentration at the bottom of a valley, because positive curvatures are like smiley faces that are positive. And so we're looking for the maximum regression coefficient, and 0.76 is a very good one. I think better than anybody had done for fatigue. And so we were happy with that, but we thought we could do better, and maybe just the maximum curvature along a profile wasn't enough. So we thought, well, let's take the average of the 10 greatest curvatures, and we did a little better. Scale changed slightly. And then we thought, well, maybe variance is important because we're just looking at one profile, and clearly what's going to be the most dangerous would be a valley that's running along the profile. So maybe we ought to look at variance as well. And we threw that in, and it got worse. And then one day I came in, and Margot was looking at an absolutely beautiful curve. And so this was largely trial and error, taking the maximum curvature plus 2 times the standard deviation. And we had 0.96, which is a wonderful R-squared experimentally, and at a very specific scale. So here's what this looks like, multi-scale regression analysis results. So here are the R-squared values from a maximum of 1, and here are the scales, and you can see it's it changes regularly, and that the scale with the highest correlation coefficient is rather narrow. So if we're very far from that scale, in other words, if we were trying to just pick scales a priori that would be good, we would have a very small chance of finding that one. So we need to do regularly, systematically, look at the scales over a large range. And so we don't know which scale is the best, try them all. And so here it was 0.96 at 610. So if we take a look at the curve that got us the 0.96, so here's the fatigue limit and here's the parameter that we got. One of the interesting things is heat treat or not, these all fell on the same line. So, and maybe this would be true of smoother surfaces, but a big deal is made in the literature of residual stresses, and theoretically it's easy just to add in the residual stress and say, well, this changes the stress that the surface is actually seeing. For these surfaces, it didn't really matter, or didn't influence the R-squared. They all are on the line, and they're all are behaving about the same. So here is a study from archaeology and James Stemp is a professor up at Keene State University in New Hampshire. And so he was wondering, so if you're a graduate student in archaeology, you may be making stone tools and then scraping something with them and then measuring them and then using that result to try to figure out what some ancient person was doing. And so here we're looking at discriminating tools that were used with different tool loading. And so here's the mean square ratio. So I don't know what material they were working against, but basalt makes a nice sort of knife or scraping thing because it breaks, as you can see, something like glass, which it kind of is. So so we can see that with a very high level of confidence, we can discriminate these if we're at the right scale. So an important archaeological finding. Yeah, so here are the two loads that were used. And I think they were scraping hides or something with those. So, okay. So here's one on teeth, some physical anthropology, or some people call it paleontology. So it's interesting to see what we can tell in anthropology about what critters were eating. And so in this case, oops, we're going along a little bit, aren't we? Okay, we're almost through, bear with me. So in this case, we can clearly distinguish people eating or animals eating hard objects and tough leaves. So this is work done by Professor Unger at the University of Arkansas. And this is not Professor Unger over here. So here's, again, some work on geography in Florida, and we're comparing different measurements here to show how the area scale analysis can tell the difference between different measurement techniques of the same topography. And so the area scale changes. These are interesting modal filter applications. So high pass and low pass. And so we're able to systematically see different surfaces from that. This was done by Gaëtan Legoic in France, and he spent some time during his doctoral work here as well. So almost over here, bear with me. So here we're using a sliding bandpass filter. Now, one of the interesting things is the parameter that I've been so critical of, average roughness, and here's root mean square, turn out to be rather good at correlating friction and forming tools, friction of sheet metal and forming tools, turn out to do a very good job of that if I restrict the scale of analysis. So all I have to do is bring those two scales between waviness and noise close enough together, and then filter, or then scan the spectrum, calculate the SA or the SQ at each position, and I can get very strong R-squared values. You can get very strong ones from the area scale analysis. So these sliding bandpass filters, what we call them, it's very much like adjusting a radio or tuning in a radio. Now, if I don't use a narrow filter, it's like trying to listen to the whole radio band at once, and nothing makes any sense if you listen to all the stations at the same time. But if I have a narrow enough bandpass filter and I place it in the right place, then the radio starts making sense. So, all right, let's broaden our discussion here as we're starting to wrap this up. So an interesting question to ask about many of the things we work on is, are we working on experiential or scientific disciplines? So experiential disciplines, knowledge acquired through experience, develop standards and best practices. And this is largely what we're looking at for most people doing surface metrology. But you can make your work stand out if you take a scientific approach. So scientific disciplines have a few simple, self-consistent rules that we're going to see in a moment that I have attempted to discern. And they can be applied to solving a wide variety of problems. They cannot be proven. They're axioms or laws, just like Newton's laws. And one of the things about these is that scientific disciplines, I learn a few principles, and then I've got a much broader knowledge. So can we discover some principles for surface metrology? And if we don't, is our surface metrology kind of like trying to do mechanics problems without Newton's laws? So here's some principles that I am proposing. One, scales. We need to measure, analyze, and characterize at appropriate scales for that application. The geometry, what we're characterizing, curvature or area, for example, must be characterized appropriately for that application, not just picking any 1930s parameter. Measurements. We just need sufficient fidelity. How can we tell? Well, if we're able to discriminate or correlate with confidence and strength, then we had a good measurement. And statistics. So many statistics are inherent in the parameters, like average roughness, but we're also doing the correlation and discrimination. But if we look at the work we did on fatigue, we're looking at extreme values. So fatigue certainly is extreme values, but if I was to look at something else like adhesion, the mean might be important. So to sum this up, surfaces are created with certain mechanisms that impart certain scales on the topography. The topography interacts with the environment for its behavior, and that interaction is at some other scales. When we measure, there's measurement scales. What was our sampling interval? What was our, how good is our sensor? And then when we do the analysis, like the filtering, we impart other scales. And so what we want to do is discriminate or correlate between correlation, topography, and behavior. So if we don't have the right scales in the characterization, which means we had to measure at the right scales, we had to analyze the right scales, we're not going to be able to figure out what was going on with the manufacturing process or how it's behaving. So these scales need to be preserved down here, and then we can do discrimination or correlation. So that you can be thinking about in your work. And there's kind of two sides to this: making the surfaces over here and then knowing how they're going to behave over there. Quick summary. So if we're looking at dimensionality in terms of fractals, we've done length, area, and to a certain extent volume. And these scale-based derivatives like length scale and area scale. We haven't done filling scale yet, so that's waiting to be developed. If we look at spatial derivatives, so the first derivative of the position spatially is the slope. Second derivative is kind of the curvature, and we can do profile or aerial. And so then the scale derivatives of these we haven't used yet. So we're trying to organize things a little bit like a periodic chart and seeing what's missing as we go through these things systematically. So curvatures on surfaces are second order tensors, making them very interesting and I think a very powerful calculation technique. So what we're looking at in Veluza's work on the fatigue was profiles, and here we're looking at actual surfaces. And this was developed by Tom Bartkowiak, who was also visiting us while he worked on his doctorate. He's from Poznan University of Technology. So he's been developing and publishing stuff on curvatures as second order tensors. So some closing thoughts. We get a new dimension if we use scales for looking for relations and with processing and performance. If we only use the default scales that are in most of the current software, sort of like going fishing at just one depth. And so we might find some, but we're going to miss a lot of them. So the message: use multiscale geometric characterizations and analyses. Future work: so we need to do more standardization and systematization with this. And so these kinds of ontologies with the map that we looked at, like a periodic table, we need to do more standardization. There's lots of correlations and discriminations, important ones that we should be looking for. And so we need to do more systematic advancement, more effective research. So there is some interesting potential, thinking of current topics, to address surfaces that can address pandemic problems. How do I make a surface that will not be friendly to bacteria or viruses, make it easy to clean, or some other surfaces that will pick those up and hold them? Then that might be some of my cleaning material. Climate change. If I want to sequester carbon, I would like large areas over which to sequester it. That depends on the topography. So as we use these different engineering and scientific techniques, here is the first canon of engineering ethics: hold paramount the safety, health, and welfare of the people, of the public. And that's what we should be doing with what we've learned. Now, if you want more on this, here is a paper that I organized with 14 co-authors internationally to look at the multiscale analyses and characterizations. So that's available in the literature. And here's some people that helped with the paper or worked on it or helped develop things. And we've been fortunate to have lots of good students who visited us from different countries. And here's some of my friends that work on surface metrology in different countries. And as in closing, I'd like to say there are, every term, we offer a course on surface metrology online. Every other year it's on campus. So every term and through the summer. So if you'd like to learn more about surface metrology and maybe design a research project based on surface metrology, you should take a look for that course. It's usually offered as a special topics. So thank you very much for your attention. And for those of you who bared with me for an extra 12 minutes, I appreciate that.
Okay, that is great.